So this is a problem that's really going to test your ability to visualize a problem and think through it critically and identifying the pieces that are relevant. So there's a lot going on in this problem to unpack, but it starts with reading it carefully and putting a visual in your mind. So Anne is driving. She's got a rate of speed, and she sees a child. Right. The moment she sees it, she can't be pressing the brakes yet. Right. She takes 0.75 seconds to react before applying the brakes. So once braking, the car will slow to a stop at a rate of 1.5 meters per second squared. And it says the child entered the road 45 meters ahead of Anne's car, and will she stop in time? All right, so there's a lot going on here, and let's start with drawing a picture and identifying how this car is moving. All right, so we have the vehicle. At the instant she sees the child. So let's roll up here. Here's our child. Right, this child is at a position of 45 meters. That's what we know. We can assume the car then is at an initial position of 0 meters. All right, that's always a good rule of thumb is wherever we start, let's just call that 0. All right, so this child's up ahead. Now, this car has a velocity of 50 kilometers per hour and is moving to the right. However, it's impossible to be hitting the brakes already. So this car is going to delay. There's a time period of 0.75 seconds during which this car is actually coasting along and not speeding up or slowing down, or at least that's what you can assume. And in that time, that car is going to be at a new position, right? And then it's going to start slowing down, right? So this car, and maybe I'll draw a new car up here. This is the new position of the car. This is the final position of the reacting time, which is also equal to the initial position of the braking period. And so now we see something happening here. All right, this car from this position is going to hit the brakes, and hopefully this car is going to finish over here. All right, that's our goal, right? Because we don't want to hit the kid, but it could finish over here, right? We don't know where the final position of this car is going to be. All right, and this is where that 45 comes into play, but we'll get to that here in a minute. So later the car is going to be at that spot. All right, but I hope you understand we got an issue here. We kind of have a bunch of these different positions. We have some different time frames, and the car's moving differently. In the first part, let's label this part 1. This car is moving at constant velocity. Which means it has no acceleration. Then in part 2, there is a leftward acceleration to slow the car down. There's something pushing on it to slow it down, right? That car is going to have the same 50 kilometers per hour when that phase starts, right? And hopefully that car is going to stop in time. So just like we've done in other problems, all right, this is uniformly accelerated motion in part 2. Because there's two kinds of motion, we have to treat them like two kinds of problems. So problem number 1, all right, we have A, T, V initial, V final, X initial, and X final. But A is 0 meters per second squared. It's constant velocity. We know the time, 0.75 seconds. It starts at 50 kilometers per hour. Now that should be a red flag. Let's go ahead and convert that. Let's get rid of kilometers and go to meters. There are 1,000 meters in a kilometer, and there in an hour, 1 hour is 3,600 seconds. Hours cancel with hours, kilometers with kilometers. We're in meters per second. All right, and so we can take 50 times 1,000 divided by 3,600, and now we're in meters per second, 13.89 meters per second. This car later, if it's not accelerating, will also be at 13.89 meters per second, right? It starts at some position and it's going to finish somewhere. All right, so again, we see the only thing we don't know right now is x final, right? And since it's constant velocity, we only have one equation for x final. Now technically, you have 1/2 at squared plus v initial t plus x initial, but because a is 0, that goes away and it becomes a simple linear equation, and I can plug right in. My velocity is 13.89. My time is 0.75 seconds, and my initial position is 0. So I can take that value times 0.75, and I know where I'm going to finish at 10.42 meters. X final is equal to 10.42 meters. So I can write that value right into here, and that's where the car is going to be located after the driver reacts. The car is going to begin hitting the brakes at that point. And now we begin part 2. A, T, V initial, V final, X initial, X final. We know it's accelerating. What direction is that arrow? Well, if we assume to the right is positive, that arrow points left. It is going to subtract speed away from the car. So it is a negative acceleration of 1.5 meters per second squared. That negative is critical. If you miss that, you're going to miss the problem. Now we don't know how long it's going to take to stop. We do know this car is still traveling at 50 kilometers per hour when we start, so 13.89 meters per second, but it's going to stop. It's slowing to a stop, which means its final velocity is 0 meters per second. Where does it start? Well, here's our bridge, right? These problems typically have a bridge between the two parts. Where I finish in the first part is now where I begin in the second. So I'm going to start at a position of 10.42 meters, and I'm going to finish somewhere. All right, and so now we need to figure out how to get to x final. And again, we have our two equations. We have x final is equal to 1/2 at squared plus v initial t plus x initial, and we have v final is equal to at plus v initial. I want x final, but I don't have time. However, I do have velocity final a and v initial, and so I can use equation 2 to get the time to stop. So I'm going to plug in v final is 0, a is negative 1.5 times t plus my initial velocity, 13.89. Can add the 1.5 t to both sides and then divide by 1.5, and I get 13.89 divided by 1.5. My time is 9.26 seconds. It's going to take almost 10 seconds for this car to stop. Seems like a long time, but maybe she didn't hit the brakes with much urgency. Hopefully she feels confident she's not going to strike the kid. So I know 9.26 seconds. And now I can use equation 1 to calculate x final. And so x final is going to be 1/2 of negative 1.5 times my time, 9.26, and that's squared, plus my initial velocity, 3.89 times 9.26, plus my initial position, the 10.42 meters. And when I calculate that all out, I get 0.5 times negative 1.5 times 9.26 is my answer, so I'll do second answer squared, plus 13.89 or 888 times my answer, which is that same time, 9.26, plus 10.42. And I get a final position of 74.72. That's not good. X final is equal to 74.72 meters. Oh, what does that mean? Oh boy, let me double check, make sure I didn't do something wrong here, because that's not a good thing. All right, if my child is located at 45 meters, right, this answer is greater than 45 meters. So to answer my question, we struck the kid. Didn't mean to be morbid here. Sometimes when you write physics problems, bad things happen. If I get an answer like this, and you're thinking, boy, Mr. Werman's pretty mean, right? He has a woman striking a kid. Well, maybe I'm going to check my work. Let's double check to see if I got everything right here. 50 kilometers per hour. Did I do my conversion right? All right, that looks correct. 13.89. All right. I multiply that by 0.75. That seems like a reasonable distance. Let's roll in here. Let's look at my time. Negative 1.5. Again, it's not a very high acceleration. She starts at a certain speed. Yeah, that seems reasonable, 9.26 seconds, and that does seem like a long time to stop. And sure enough, when we plug these things in, did I square my 9.26? Maybe that's my issue. I sure did. My answer was squared in here. So I believe, unfortunately, we struck the kid. All right, so again, the 45 is not used in any calculation. However, it is used as a point of comparison to what I got for X final. All right, had I gotten an X final of less than 45, then I would know that the kid was safe. So hopefully this gives you a good idea. It's pretty in-depth problem. There's a lot of components to it that might trip you up, but I think you're starting to get a sense of having a plan and an organization, these ATVX tables, to help identify what you have and what your next step can be. And if you follow this process, I think that you're going to have some success.